Today we'll be discussing JEE Advanced 2021 Mathematics Paper 1. Now the first question is, consider three sets E1, 1, 2, 3, F1, 1, 3, 4 and G1, 2, 3, 4, 5. Two elements are chosen at random without replacement from the set E1 and let S1 denote the set of these chosen elements. Let E2 be E2 minus S1 and F2 be F1 union S1. Now two elements are chosen at random without replacement from the set F2 and let S2 denote the set of these chosen elements. Now G2 is G1 union S2 and finally two elements are chosen without replacement from the set G2 and let S3 denote the set of these chosen elements. Now let E3 equals E2 union S3. Now if it is given that E1 equals E3, find the conditional probability of the event S1 equals 1 by 2. We need to find the value of this conditional probability. Now we are given three sets E1 and E1 is 1, 2, 3. We have F1 and F1 is 1, 3, 4. And then we have this G1 which is 2, 3, 4 and 5. Now first we choose two elements from the set E1 to form this set S1. Now we can choose this S1 in three ways. So this S1, it can be either 1, 2 or 2, 3 or 1, 3. Now it is given that E1 is equal to E3 and E3 is E2 intersection of S3 and E2 is E1 minus S1. So E2 is the remaining element from E1 and if E3 is equal to E1, it simply means that this S3, it must be equal to S1. So this S3, in the first case, it should be 1, 2. In the second case, it should be 2, 3. And in the third case, it should be 1 and 3. So we have three cases, case 1, case 2 and case 3. Now it says we are taking F2 which is F1 union S1. So we'll write F2 which is F1 union S1. Now in the first case, this union will be 1, 2, 3, 4. In the second case, it will be 1, 2, 3, 4. And the third case, it will be 1, 3 and 4. Now from this, we have to choose S2 and then from G1 union S2, we have to form G2 from which we have to select S3. Now since G1 has 2, 3, 4 and 5 and S3 has 1, 2. So in the first case, this should have this G1 intersection S2. It should have 1, 2, 3, 4 and 5. In the second case, when it is 2, 3, there can be two cases possible. Either it will be 1, 2, 3, 4, 5 or it will be 2, 3, 4 or 5. And in the third case, since it has 1 here, it should be 1, 2, 3, 4 and 5. Now in this first case, if we have to select these two elements in S2, then one of the element, it must be 1 and the other element, it could be any one of 2, 3 and 4. Now here also, if we choose this first case, then it should be 1 and then some element X. And if it is second case, then it should be some elements X and Y other than 1. And in this third case, it should be this 1 and then some element X. So these are the four cases possible in which E1 is going to be equal to E3. Now we'll start calculating. Now in this first case, if we calculate this probability and say it is P1, then first we need to choose two elements from these three elements. It can be done in 2C2 upon 3C2 ways. Then from this set, we have to select S2 in such a way that 1 is always included. So total number of ways is 4C2. And if 1 is always included, then it will be 3C1. Now from this, we have to select S2, which is 2C2 upon 5C2. So this probability will be 1 by 3 and this is 3 by 6 and this is 1 by 10. So it is 1 by 60. So this first case, it is 1 by 60. Now before the second case, we'll calculate actually this third case. In this third case, suppose this is P3. Now first we have to select 1, 3, which again can be done in 1 by 3 ways. Now again for S2, we have to select 2 elements from these 3 elements. It can be done in 3C2 ways, and one of the element, it must be 1. So this other element, it can be selected in 2C1 ways, and then into these 2 out of 5. So it will be 2C2 upon 5C2. Now this is 1 by 3 into 2 by 3 into 1 by 10, and it will be 1 by 45. Now we'll come to this second case when we have this 2, 3. So this is P2 and it'll be this 1 by 3 into, now we have 2 cases. Case 1, if 1 is included, now if 1 is included, there'll be 3C1 upon 4C2 into, now from this we need to select 2, 3. So it'll be 2C2 upon 5C2 plus, and if 1 is not included, then it'll be any 3C2 upon 4C2 into, now this is 2C2 upon 4C2. Now it'll be 1 by 3. Now this is 3 by 6 and this is 1 by 10 plus this is 3 by 6 into 1 by 6. Now this is 1 by 2. So we'll take this 1 by 2 common. So it'll be this 1 by 6 and then 1 by 10 plus 1 by 6, which is 8 by 180, and which is 2 by 45. So this probability is 2 by 45. So in the first case, we get this probability as 1 by 60. In the second case, it is 1 by 45. And the third case, it is 2 by 45. Now we need to find this conditional probability that if E1 equals E3, S1 is 1, 2. So this required probability P will be given by P1 upon P1 plus P2 plus P3. Now this is 1 by 60 and it is 1 by 60 plus 1 by 45 plus 2 by 45. So this is 1 by 60. Now this is 1 by 60. Now this is 3 by 45 and 3 by 45 is 1 by 15. Now this is 4 by 60. So this probability will be 1 by 5. So the value of this conditional probability is 1 by 5 and that's your option A. Question number 27. It's a standard Bayes theorem question. We are given that some person is allergic to certain thing and there is a test for that. So this test, it is known to give the following result. For people who really do have the allergy, the test says yes 90% of the time. And for people who do not have the allergy, test says yes 15% of the time. If 2% of the population have this allergy and the test says yes, what is the chances that this person does really have the allergy? Now this person can have the allergy or does not have the allergy. So what is the probability of having the allergy? Probability of having the allergy is simply 2 by 100 and not having allergy is 98 by 100. Now probability that the report confirms yes if the person has allergy is 90%. So it will be simply 90 by 100, and the probability the report confirms yes if the person doesn't have allergy is 15%. So there will be 15 by 100. Now we need to find the probability that this person does really have the allergy. We'll take this case when the person has the allergy in the numerator and then total case in the denominator. We'll have this result as 2 into 100 into 90 upon 100 divided by 2 into 100 into 90 upon 100 plus 98 upon 100 into 15 upon 100. So this 100 will get cancelled. Now we'll cancel this 15 also. So it'll be 6 and 6. So it'll be simply 12, and this is 12 plus 98. So it should be 12, and then 12 plus 98 is 110. It'll be simply 6 by 55, and that's your option number B. Today we'll discuss Indian Statistical Institute, that is ISI's BMath and BStat 2018 paper. Link to that paper, I'll provide it in the description below. Now again, questions in this paper, they're absolute delight. So let us get on with the first question. And the first question is, let x be a number that lies between 0 and 1 by 6. When a certain biased die is rolled, a particular face f occurs with probability 1 by 6 minus x, and its opposite face occurs with the probability 1 by 6 plus x. So we have this die where these two opposite faces, one of the probability is 1 by 6 minus x, and for the other it is 1 by 6 plus x, and for the remaining four faces the probability is simply 1 by 6. Now it also says, recall that opposite faces sum to 7 in any dice. So that means these two faces, it can be either 1 or 6 or 2 or 5 or 3 or 4, or they're ordered pairs, that is 6 1, 5 2 or 4 3. Now it says if the probability of getting the sum 7 is 13 by 96, we need to find the value of x. Now we need to find probability of getting the sum 7. So probability of getting the sum 7 is when we get either 1 6 or 6 1 or 2 5 or 5 2 or 3 4 or 4 3. Now out of these 6 pairs, there is exactly one pair with these probabilities 1 by 6 minus x and 1 by 6 plus x, and for the remaining 4 pairs it will simply be 1 by 6 and 1 by 6. So I can simply write it as 2 times 1 by 6 minus x into 1 by 6 plus x, and then plus 4 times it will be 1 by 6 into 1 by 6, and they have given that this probability is equal to 13 by 96. So I can write it as, so this is 2 and this is 1 by 6 square minus x square, and then plus 4 by 36 equals 13 by 96. So here will be 2 by 36 plus 4 by 36. 6 by 36 is simply 1 by 6 minus 2x square, and this is 13 by 96. So I can write 2x square as 1 by 6 minus 13 by 96. So it will be 96, and then this is 16 minus 13. So I'll write it as 2x square equals 3 upon 96, which is x square equals 1 by 64. So this value of x should be 1 by 8. That's your option number A. Now question number 3, part A is, let x be chosen at random from the interval 0 to 1. What is the probability that greatest integer function of log 4x to the base 10 equals greatest integer function of log x base 10. Now they're equal, and suppose they're equal to some number, say r. Now when greatest integer function of x is equal to r, then x lies between r and r plus 1. So for this first part we can write this log 4x to the base 10, it will lie between r and r plus 1. Now if we take anti-log, we can write 10 to the power r divided by 4, it will be less than or equal to x, and it will be less than 10 to the power r plus 1 divided by 4. And the same way we can write it for the second part. Again, this log x base 10 will lie between r and r plus 1. So it will be greater than 10 to the power r but less than 10 to the power r plus 1. Now there is an AND condition between these two results. So if we take intersection of both the conditions, we'll get x should be greater than 10 to the power r, but it should be less than 10 to the power r plus 1 by 4. Now we can write 10 to the power r plus 1 by 4 as 5 by 2 into 10 to the power r. So these two greatest new functions, they'll be equal when x lies between 10 to the power r and 5 by 2 10 to the power r. Now if we find length of this interval, say LR, then length of this interval LR will be 5 by 2 10 to the power r minus 10 to the power r, which is 3 by 2 into 10 to the power r. Now we have to find length of all such intervals for which the value of x will lie between 0 and 1. So this x, it must lie between 0 and 1. Now 10 to the power r, it is greater than 0 for all r belongs to r, and then 5 by 2 10 to the power r will be less than 1 if 10 to the power r, it is less than 0.4, that is when the value of r is less than or equal to minus 1, where r is an integer. So from these two conditions, we'll get this r will take the value starting from minus 1, minus 2, minus 3 up to minus infinite. Now we need to find this required probability. Now for this probability, the sample space, it corresponds to length of this interval. So length of sample space, it is simply 1. Now we need to find our favorable length, which corresponds to all these cases. So our favorable length L will correspond to this summation LR, where R varies from minus 1 to minus infinite. So it will be 3 by 2 10 to the power minus 1 plus 10 to the power minus 2 10 to the power minus 3, and this series will continue up to infinite. Now this is nothing but a GP. So it will be 3 by 2 A upon 1 minus R, which is 3 by 2 into 1 by 9, which is 1 by 6. So from geometrical probability, we can say that this required probability of this event, say A, is given by small l upon capital L, which is 1 by 6 upon 1. So this required probability is 1 by 6. Today we'll discuss CMI's 2017 paper, and the first question is, positive integers A and B possibly equal are chosen randomly from among the divisors of 400. The numbers A and B are chosen independently, each divisor being equally likely to be chosen. We need to find the probability that GCD of AB is 1 and LCM of AB is 400. Now first we look at number of divisors of 400. Now we know that 400 is 25 into 16, so there will be 2 to the power 4 into 5 square. So we know that if we have any number n which is expressed as prime powers like p1 to the power a, p2 to the power b, p3 to the power c, number of divisors is given by a plus 1, b plus 1, c plus 1 and so on. So in the case of n100, number of divisors in the case of 400 is 4 plus 1, which is 5, and then 2 plus 1, which is 3. So in total we have 15 divisors of 400. Now it says two positive integers A and B are chosen from these 15 divisors and they can be possibly equal. So that means we can choose one number more than once. So we'll find total number of choices for AB. So total number of choices for A and B will be, so first we look at total number of choices for A. We have 15 choices for A, and the same way we have 15 choices for B. So altogether we have 225 choices. Now we need to find this probability that these numbers are chosen such that their GCD is 1. That means there is nothing common between A and B, and LCM of AB is 400. This simply means that A and B are co-prime factors of this number n. So we are looking for co-prime factors. Now how do we split 400, which is 2 to the power 4 into 5 square, in two co-prime factors? So for co-prime factors, we know that each of these terms 2 to the power 4 and 5 square, they must go to either A or B. So that means for this 2 to the power 4, we have two choices. Either it will go to A or it will go to B. In the same way, 5 square, again we have two choices, either A or B. So we have two choices for 2 to the power 4. We have two choices for 5 square. So total number of co-prime factors is simply 4. If we want to write co-prime factors, then we can write them also. Suppose we have A and B. Now A can be 1, B can be 2 to the power 4 into 5 square. This could be 2 to the power 4, B could be 5 square, or we can reverse them. It could be 5 square and 2 to the power 4, or it could be 2 to the power 4 into 5 square, and here B could be 1. So we have four possible ways in which we can split this number n into co-prime factors. So this required probability is favorable case, which is 4, upon total number of case, which is 225. So this probability is simply 4 upon 225. Now question number 5 is, you are given an 8 cross 8 chessboard. If two distinct squares are chosen uniformly at random, find the probability that two rooks placed on these squares attack each other. We know that a rook can move either horizontally or vertically in a straight line. So we have this 8 cross 8 chessboard, and we need to find the probability that these two rooks placed, they will attack each other. Now we need to find this probability. Suppose the event is A, so we need to find probability of this event A. Now first we'll find total number of ways in which we can place two rooks on these two squares. So altogether there are 64 squares, and from these 64 squares, we need to select any two squares to place these two rooks. So it can be done in 64C two ways. Now we need to find the probability that these two rooks, they'll attack each other. So we know that these two rooks, they'll attack each other if they are placed on the same horizontal file or if they are placed on the same vertical file. So we'll take this case 1 when the two rooks are on same horizontal file. So we have 8 files. So from these 8 files, we can select any one file, and it can be done in 8C1 ways. Now once we have selected any file, then on this file, if we'll select any two squares, then these two rooks, they'll be attacking each other. So from these 8, we'll need to select any two squares, and it can be done 8C2 ways. Now plus, we can also place these rooks vertically. Now we'll have to place them vertically, then we'll have to choose a vertical file. So we have 8 vertical files. So from these 8, again we'll select any one. So it is 8C1, and again on this selected file, we can place these rooks on any two squares, and it can be done 8C2 ways. Now this is 8C1, which is 8. Now 8C2 is 8 into 7 divided by 2. So it will be 28 into 2, because both the values, they'll be same, upon 64 into 63 into 2. So 8, 864, 4, 4, 14, this is 2 and 9. So the probability that these two rooks will attack each other is simply 2 by 9. Now question number 23, it's a Bayes theorem question. It says a bag contains some candies, 2/5 of them are made of white chocolate and 3/5 are made from dark chocolate. So we have two kind of chocolates. So some of them, they are white and some of them, they are dark. So the probability that we get a white chocolate is 2 by 5, and the probability of getting a dark chocolate is simply 3 by 5. Now out of white chocolates, 1/3 are wrapped in red papers. So these chocolates, they're wrapped in either red papers or blue paper. So the probability that white chocolate, they're wrapped in red paper is 1 by 3, and it is wrapped in blue paper will be 2 by 3. In the same way, for dark chocolate, The probability that it is wrapped in red paper is 2 by 3 and probability that it is wrapped in blue paper is 1 by 3. Now it says if a randomly selected candy from the bag is found to be wrapped in red paper, then what is the probability that it is made up of dark chocolate? So it is a Bayes theorem question. So we need to find the probability that it is made up of dark chocolate when it is wrapped in red. So that means we need to find this probability that it is dark when it is wrapped in red. So we'll put this case when it is a dark chocolate and with red paper in the numerator. So it will be simply 3 by 5 into 2 by 3, and in the denominator we'll put the probability of getting a red paper. So we'll get a red paper when it is white and red or when it is dark and red. So here will be 2 by 5 into 1 by 3 plus 3 by 5 into 2 by 3. So this probability of getting a dark when it's a red paper is, so this is 6 by 15 and here it is 8 by 15. So it is simply 3 by 4 and that's your option number B. Now we'll come to the section B and the first question is, out of 14 students taking test, 5 are well prepared, 6 are adequately prepared and 3 are poorly prepared. So we have 3 set of students. So suppose event W, it has set of well prepared students, A set of adequately prepared and then P set of poorly prepared students. The probability of choosing a student from the set of well prepared will be simply 5 by 14. Adequately prepared will be 6 by 14 and poorly prepared will be 3 by 14. Now there are 10 questions on the test paper. A well prepared student can answer 9 questions correctly. An adequately prepared student can answer 6 and a poorly prepared student can answer only 3 questions correctly. Now for each probability below, write down your final answer as a rational number in lowest form. If a random student is asked 2 distinct random chosen questions from the test, what is the probability that student will answer both questions correctly? Let us say event C is student answers the question correctly. Now if the student is well prepared, then the answers will be correct with the probability 9C2 upon 10C2. Now if the student is adequately prepared, then the probability of getting 2 questions correct is 6C2 upon 10C2, and if it is poorly prepared, then the probability of getting 2 correct is 3C2 upon 10C2. Now we need to find the probability that a student will answer both questions correctly. So it is conditional probability question. The probability that student will answer a question correctly is when we multiply each of these corresponding probabilities. So it will be 5 by 14 into 9C2 upon 10C2 plus 6 by 14 into 6C2 upon 10C2 plus 3 by 14 into 3C2 upon 10C2, which is 31 by 70. Now part B is, suppose the student was chosen at random and asked 2 selected questions from the exam and did answer both questions correctly. Find the probability that chosen student was well prepared. Now this is Bayes theorem question. So if the student is well prepared, then we'll take this case in the numerator. If the questions are answered correctly, then the student is well prepared. It will be 5 by 14 into 9C2 upon 10C2 upon 31 by 70. So it will be 20 by 31. Now here the question is, a mother and her 2 daughters participate in a game show. At first, the mother tosses a fair coin. If the result is heads, then all 3 win individual prizes and the game ends. And if the result is tails, then each daughter separately throws a fair die and wins a prize if the result of a die is 5 or 6. Now first, mother tosses a coin, and if she gets heads, then all of them, they win. And if it is tails, then both the daughters, they roll a die, and if they get 5 or 6, they win, else they lose. So for both of them, we'll have these conditions. Now getting a heads, it is 1 by 2. Getting a tail, probability is 1 by 2. Daughter 1 winning, her probability is 1 by 3. Losing is 2 by 3. And the same way for second daughter, it will be 1 by 3 winning and 2 by 3 losing. Now the first question is, suppose the first daughter did not win a prize then what is the probability that second daughter also did not win a prize? So we need to find this conditional probability that second daughter did not win a prize when first one did not win. So we'll have this probability as probability of D1 intersection D2 upon probability of D1. Now both of them, they'll not get a prize only when if it is tails. So if it is tails, we'll get 1 by 2, and then both of them, they independently do not get 5 or 6. So it will be 2 by 3 into 2 by 3. Now divided by probability of first daughter not getting a prize. Again, it will be this 1 by 2, and she won't get a prize if the probability is 2 by 3. So it will cancel. So answer to this first part is simply 2 by 3. So if first daughter did not win a prize, the probability that second daughter will also not win a prize is 2 by 3. Now in the part B it says, suppose the first daughter won a prize, what is the probability that second daughter also won a prize? We need to find this probability that second daughter wins the prize if first one wins the prize. So it will be this probability W1 intersection W2 upon probability of W1. Now probability of W1 is either when we get heads, so it will be this 1 by 2, or when it is this 1 by 2 and she gets 5 or 6, so it will be this 1 by 3. And the case when both of them wins, it could be this first case when it is 1 by 2, or the second case when they get tails, both of them they won a prize, so it will be 1 by 3 into 1 by 3. Now this 1 by 2 will cancel, so we'll get this as 1 plus 1 by 9, and there will be 10 by 9 divided by, now this is 1 plus 1 by 3, and there will be 4 by 3. Now this is 3, it will be simply 5 by 6. So the probability that second daughter also won a prize, provided first daughter wins it, is 5 by 6. Now question number 11 is, there are 4 distinct balls labeled 1, 2, 3, 4 and 4 distinct bins labeled A, B, C, D. The balls are picked up in order and placed into one of the 4 bins at random, and let EI denote the event that first I balls go into distinct bins. Now calculate the following probabilities. Now first is, we have to find this probability that event is E4, and when the event is E4, that means all the 4 balls, they went into different bins. So first we have to find total number of cases. So we have 4 balls, and for each ball we have 4 choices. So total number of ways will be 4 into 4 into 4 into 4, 4 times. So it will be simply 4 to the power 4. And now if all the 4 balls, they go into different bins, then we just have to arrange these 4 balls in 4 places, and it can be done in simply factorial 4 ways. So this probability will be simply factorial 4 upon 4 to the power 4. Now second one is this conditional probability. We have to find probability of E4 when it is given that E3 has already occurred. So it will be probability of E4 intersection E3 upon probability of E3. Now what is E4 intersection E3? E4 intersection E3 is nothing but it is simply E4, and here will be simply E3. Now probability of E4 is factorial 4 upon 4 to the power 4, and probability of E3 is probability of the event that first 3 balls, they go into different bins. So first we have to select which bin. So it will be 4C3 and then factorial 3, and for the last ball we have 4 choices. So it will be 4 upon 4 to the power 4. So this 4 to the power 4 will cancel. Now this factorial 4 will cancel. So it will be simply 1 by 4. Now this third one is probability of E4 upon E2. Now it will be probability of E4 intersection E2 upon probability of E2, which again is probability of E4 upon probability of E2. Now this is factorial 4 upon 4 to the power 4, and probability of E2 is first 2 balls, they went into 2 different bins. So it will be 4C2 into factorial 2, and then for the remaining two balls it will be 4 square and then 4 to the power 4. Here this 4 to the power 4 will cancel. So we can write this as 4 into 3 into 2, and here will be 6 into 2 into 16. So this 6 will cancel, 2 will cancel, and this is simply 1 by 8. Probability of E4 upon E2 is 1 by 8. And then finally this probability of E3 upon E4 will be probability of E3 intersection E4 upon probability of E4. Now probability of E3 intersection E4 is probability of E4 and L B upon probability of E4, which is 1. So this is a sure event. So the required probabilities are factorial 4 upon 4 to the power 4, 1 by 4, 1 by 8 and 1. Now question number 52 is, two coins are tossed independently where probability head occurs when coin I is tossed is Pi. It is given that at least one head has occurred. What is the probability that coin produced different outcomes? So we need to find this probability that it produced different outcomes when we know that at least one of them is a heads. Now when we say at least one of them is a heads, it will be probability of H1 plus probability of H2 minus probability of H1 intersection H2. Now, what is the probability that the coin produced different outcomes when at least one head has occurred? So either it could be first is heads and second is tails, or first is tails and second is heads. Now these probabilities, they are independent. So we can write probability of H1 as P1 and then probability of second tails is 1 minus P2, and in the same way it is 1 minus P1 and it will be simply P2 upon this is P1 plus P2, and then P intersection B is P into PB. So it will be P1 into P2. So we can write this as P1 plus P2 minus 2 P1 P2 upon P1 plus P2 minus P1 P2, and that's your option number B. Now question number 53 is, the number of cars X arriving at a service station per day follows a Poisson's distribution with mean 4. So value of lambda is 4. Now it says the service station can provide service to a maximum of 4 cars per day. Then the expected number of cars that do not get service per day equals what? Now what we'll do is we'll define a random variable X equals I, and then we'll find its corresponding probability Pxi. And then we'll also define a random variable XR, which represents number of returned cars. If I is 0, then XR is 0. If I is 1, then again it is 0. So if it is 0, 1, 2, 3, 4, then number of returned car will be simply 0. But when we have more than 4 cars, now 1 will be returned, for 6 it will be 2, for 7 it will be 3, and then we have their corresponding probabilities, which are probability X equals 5, probability X equals 6, probability X equals 7. So we can write expected number of returned car will be 0 into Px equal to 4 plus 1 into Px equals 5 plus 2 into probability X equals 6, and it goes up to infinite, which we can write as I into P X equals I plus 4, where the value of I varies from 0 to infinite, and that's your option number C. Now question number 16 is, consider a large village where only 2 newspapers P1 and P2 are available to the families. It is known that proportion of families not taking P1 is 0.48. So probability that a family doesn't take P1 is 0.48. That means probability that family takes P1 will be 1 minus 0.48 and will be simply 0.52. In the same way, proportion of families not taking P2. So that is P2 not, it is 0.58. That means probability that a family takes P2, it is 1 minus 0.58, it will be 0.42. Now the next one is proportion of families taking only P2. So that means this is P2 intersection P1 naught. So we know that it is given by P2 minus P1 intersection P2, and this value is simply 0.30. Now probability of P2 is 0.42. So this is 0.42 minus probability of P1 intersection P2, and this is 0.30. So from here we can write P1 intersection P2 will be simply 0.12. Now we need to find the probability that a randomly chosen family from village takes only P1. So that means we have to find probability of P1 intersection P2 naught. So it will be probability of P1 minus probability of P1 intersection P2. So probability of P1, it is 0.52 minus probability of P1 intersection P2, it is 0.12. So it will be simply 0.40, and that's your option number C. Now the 17th question is, there are 8 coins, 7 of which have the same weight and the other one weighs more. So let the coins be A, 7 times. They are identical coins, and then we have this other coin which weighs more than remaining 7 coins. Now in order to find a coin, a person randomly chooses 2 coins and put 1 coin on each side of common balance. If the 2 coins are found to have the same weight, the person then randomly chooses 2 more coins from the rest and follows the same method as before. We need to find the probability that the coin will be identified at the second draw. So that means in the first draw, we must get 2 identical coins. So here this probability will be 7C2 upon 8C2. Now in the next one, we must have 1 identical coin and this 1 distinct coin. So from these remaining 5, we'll select 1 and then we'll get this as 1C1 divided by 2 from any remaining 6. So this is 7, 6 and it is 8, 7. This is 5 and this is 6, 5 into 2. So this 5 will cancel, 6 will cancel, 7 will also cancel. So this probability will be simply 1 by 4, and that's your option number C. Question number 18 is, let A1, A2, A3 and A4 be the vertices of a square. So we have this square which is A1, A2, A3 and A4. Now particle starts from A1 at a time t equals 0 and it can move to either A2 or A4 with equal probabilities. Suppose this probability is P. So this P is 1 by 2. Now we need to find this probability when t is 4, where t is the minimum number of steps required to cover all the 4 vertices. Starting from A1, it will cover all the 4 vertices when from A1 it goes to A2, from A2 it goes to A3, A3 it goes to A4, and then from A4 it goes to A1, or from A1 to A4, A4 to A3, A3 to A2, and then A2 to A1. Now moving in any direction, it is an independent event. So from A1 to A2, it will be P, A2, A3, it will again be P, it will be P, and then P. So from A1 to A1, using this first route, it will be simply P to the power 4. In the same way, the probability of particle moving from A1 to A1 will again be P to the power 4. So the probability that this Pt equals 4 will be 2 times P to the power 4, where the value of P is 1 by 2. So it will be simply 1 by 8, and that's your option number C. Now question number 19 is, let x1, x2 and xn be independent and identically distributed with pxi equals 1 equals pxi equals minus 1 equals p, and then pxi equals 0 as 1 minus 2p for all I from 1 to n. Then we have defined an as this probability x1, x2, xn is equal to 1. Second one is bn, which is x1, x2, xn as minus 1. And this third one where x1, x2 into xn, it is equal to 0, and we have taken it as cn. So for any random variable xi, there are 3 choices. Either it will be 1, 0 or minus 1. and their corresponding probabilities are P, 1 minus 2P and P. Now since it represents a binomial distribution, 1 minus 2P should be greater than 0, that is value of P should be less than 1 by 2. Now first we'll talk about AN. Now AN is this probability x1, x2 into xn and it is equal to 1. Now first we need to find in how many ways we can choose x1, x2 and xn such that its product is 1. Now one of the way of choosing it is when all the values they are 1. So if all the values they are 1, then we have only one case. Next one could be when n minus 2 values are 1 and then 2 values are minus 1. Then again their product will be 1. So from these n, we need to select 2 which will have the value minus 1. So it will be simply NC2. Next one will be all ones except 4 minus 1s. Here it will be simply NC4. It will continue till we have maximum number of minus 1s possible. Now since all these distributions they are independent, then we know that in any scenario Px1 x2 into xn will be Px1 into Px2 into Pxn. It will be simply P into P into P n times, because for plus 1 this probability is P and minus 1 also this probability is P. For each of these conditions this probability will be P into P into P n times, and that should be P to the power n. So now we can write AN. So this AN will be, now this first one it is NC0 P to the power n. Second one will be NC2 P to the power n. NC4 P to the power n. So we'll get this condition as NC0 plus NC2 plus NC4 into P to the power n. Now we know that the value of this binomial series is 2 to the power n minus 1. So it will be 2 to the power of n minus 1 into P to the power n. So it will be 1 by 2 into 2P to the power n. Now we'll take this limit n tends to infinite an will be 1 by 2 and then 2P to the power n. Now 2P is less than 1. So if 2P is less than 1, then 2P to the power infinite will be simply 0. So value of an, it tends to 0. Now in the same way, we can prove the result for Bn. So for Bn, we'll start with minus 1, and then we'll replace minus 1s with plus 1s. So we'll again end up getting the same expression. So from symmetry, we can say this Bn tends to 0. So An tends to 0 and Bn tends to 0. Now we know that either this product will be plus 1 or this product will be minus 1 or this product will be 0. That means sum of An plus Bn plus Cn will be 1. Now limiting value of An and Bn, it is already 0. So from here we can say limiting value of Cn will then be 1. So answer to this question will be An tends to 0, Bn tends to 0 and Cn tends to 1, and that's your option number D. Now question number 20 is, consider a set of all functions from this set from 1 to m to 1 to n where n is greater than m. If a function is chosen from this set at random, find the probability that it will be a strictly increasing function. So we need to find this probability. So first we'll find total number of functions that can be defined from this set containing m elements to the other set containing n elements. Now for each element we have n choices. So it will be n into n into n, m times. So total number of functions will be simply n to the power m. Now in the numerator we'll need to find total number of strictly increasing function. Now if it is strictly increasing function, then that function will be a 1-1 function. So for these m elements we'll need to choose m elements from this set containing n elements, which can be done in n, c, m ways. Now once we have selected these m elements, then we have to map them in an increasing order. So there is only one arrangement possible for all these numbers. So this probability will simply be NCM upon n to the power m, and that's your option number A. Now question number 10 is, the chance of student getting admitted to colleges A and B are 60% and 40%. So probability of getting admission in college A is 0.6 and probability of getting admission in college B is 0.4. Now, if a student is told that he has been admitted to at least one of the colleges, what is the probability that he has got admitted to college A? So we know that if A union B has already happened, we have to find this conditional probability A upon A union B. Now, probability of A intersection A union B is simply probability of A, and here will be probability of A union B. So it will be probability of A, and then probability of A union B will be probability of A plus probability of B minus probability of A intersection B. Now, getting admitted in any college, it is an independent event. So it says the colleges admit students independently. So we know that PA intersection B will be PA into PB. So we'll write this as probability of A upon probability of A plus probability of B minus probability of A into probability of B. Now, what's probability of A? It is 0.6, and here it will be 0.6, 0.4 minus 0.6 into 0.4, it will be minus 0.24. So it will be 0.6 and 1 minus 0.24. So it will be 0.76. So it is nothing but 15 by 19, and that's your option number D. Now question number 22 is, a coin with probability P of getting heads is tossed until a head appears for the first time. If the probability that number of tosses required is even, this probability is 2 by 5, we need to find value of P. Now we know that if the number of toss required is even, then it should be either not head and then head at the second toss, or not head, not head, not head, and then heads at the fourth turn, or heads at the sixth turn, and this series will continue up to infinite, and this probability must be equal to 2 by 5. Now we know that this is nothing but an infinite GP. So sum of an infinite GP is P dash upon 1 minus, now what is the common ratio? Common ratio is P bar square, and this is equal to 2 by 5. Now we know that complement of P is simply 1 minus P, and here it should be 1 minus P square upon 2 by 5. Now we'll use A plus B, A minus B. We'll get this as P 1 minus P, and then P 2 minus P, and this is 2 by 5. Now P and P will cancel. We'll get 5 minus 5P, and it will be equal to 2 into 2 minus 2P. So it will be 3P is equal to 1. So value of P is simply 1 by 3. And that's your option number B. Now question number 23 is, consider two independent events with the same probability P. The probability of occurrence of at least one of the two events is. So we'll take this probability as F, some function of P, and we'll need to find probability of A union B. So it'll be probability of A plus probability of B minus probability of A intersection B. Now both these probabilities, they are same, so it is P plus P and then minus. Now since these two events, they are independent, we know that PA intersection B is PA into PB, so it will be simply P square. So this probability will be 2P minus P square, which is nothing but a parabola opening downwards, which is always concave down. So it is strictly concave in P, and that's your option number C. Now question number 13 says, a box contains exactly 5 chips, 3 red and 2 white. Now it says chips are randomly removed one at a time without replacement until all the red chips are drawn or all the white chips are drawn. What is the probability that last chip drawn is white? Now this last will be white if we get white in first two, or if we get white red and white in third, or if we get white red red and white in fourth. These are 3 possible cases. Required probability will be, now this is white into white. Now probability of drawing a white chip is 2 by 5 into 1 by 4 plus, in this case it will be 2 by 5, red is 3 by 4, and then white is 1 by 3 into, now this we have two cases, WRW or RWW. So we have to multiply it with 2 and then plus, here it will be 2 by 5, 3 by 4, 2 by 3 into 1 by 2, and here we have factorial 3 upon factorial 2 possible combinations of WRR, so it will be 3, so we have to multiply it with 3. So this value will be simply 1 by 10 plus, now here 3 will cancel, it will also cancel, so this is 1 by 5, here this 4 will cancel, 3 will cancel, and we'll get this as 3 by 10. So it will be 4 by 10 plus 2 by 10. So it will be simply 6 by 10, which is 3 by 5, and that's your option D. Now question number 14 is, there are 7 horses in a race. Mr. Murthy selects 2 horses at random and bets on them. What is the probability that Mr. Murthy selected the winning horse? Now total number of ways in which Murthy can select 2 horses is 7C2. Now we need to find this probability that he has selected the winning horse. That means one of the horse, it must be the winning horse, and then he can choose this other horse in 6C1 ways. So it will be simply 6, and then here will be 7 into 6 into 2, which is 2 by 7. So this required probability is 2 by 7, and that's your option B. Now in part B it says 2 squares are chosen at random on a chessboard. What is the probability that they have a side in common? So if we look at a chessboard, then now there are 4 corner squares. So the probability of choosing any one square from these 4 corner squares is 4 by 64. And if we choose corner square, it has 2 neighbors. So if 2 squares, they have a side in common, then we need to choose any one of these 2. So it can be done in 2 by 63 ways. Now next we have the squares which are on the edges, but other than corner squares. Now we have 6 here. We'll have 6 on this side, 6 on this side, and 6 on this other side. So in all, there will be 24 such squares. The probability of choosing any one square from these 24 squares is 24 by 64. Now for each of these squares, we have 3 neighbors, 1, 2, and 3. So we need to choose any one out of 3, which can be done in 3 by 63 ways. And then plus, if we choose any of these squares from remaining squares, now total number of remaining squares will be 6 into 6, 36. So probability will be 36 by 64 into, so each of these squares has 4 neighbors. So we can choose any one out of 4. It can be done in 4 by 63 ways. So this required probability is 4 into 2, 8 plus 72 plus 144, which is 224 upon 64 into 63. Now this is 16 and 8, and this is 8, and this is 7 and 2, and this is 9. So this required probability is simply 1 by 18, and that is the answer to this question. Now part B is 2 distinct integers a and b. They are picked up from this set 1, 2, 3, 4 up to 100 and multiplied. What is the probability that resulting number has exactly 3 factors? Now we know that any number, it will have exactly 3 factors if and only if it is square of some prime. In that case, number of factors will be simply 2 plus 1. In all other cases, it can't be done. So that means out of a and b, one of the number, it must be 1. Either a must be 1 or b must be 1. And the other number, it must be perfect square of some prime. So this b, it can be either 2 square, 3 square, 5 square, and 7 square. After 7 square, the number will be greater than 100. And if b is 1, then a can be 2 square, 3 square, 5 square and 7 square. So this required probability is total number of favorable cases. So total number of favorable cases we have is 8, and total number of cases is we can choose A and B in 100 into 99 ways, which is 2 upon 25 into 99, and that is the answer to this question. Now question number 5 is the carbonitrided bushes need to meet the specifications on surface finish, case depth and dimensional variation. Otherwise, the bush is considered as a defective bush. Now, we have a batch of 240 bushes, and out of them, 30 do not meet the specification on surface finish. So, the probability that the bush is not going to meet surface requirement is 30 by 240. And if it doesn't meet case depth requirement, that is PEC, probability is 15 by 240, and dimensional variation, suppose PD, will be 9 by 240. Now it says 6 on both surface and case. So that means this probability of S intersection C, it will be 6 by 240. Surface and dimensional, S intersection D, it will be 4 by 240, and 4 on case depth and dimensional variation. So C intersection D is also 4 by 240. Now it says there is no bush not meeting specification for all three. So that means probability of S intersection C intersection D, it is 0. Now we need to find the chance that a bush randomly selected from the batch will be a defective bush. Now a bush will be defective if it has a problem in either surface finish or case depth or dimensional variation. Now this is equal to PS plus PC plus PD. So it will be 30 by 240 plus 15 by 240 plus 9 by 240, and then minus S intersection C, 6 by 240 minus 4 by 240 and minus 4 by 240 plus 0, and which comes to 40 by 240, and which is 1 by 6. So the chance that a bush randomly selected from the batch will be a defective bush will be 1 by 6. Now it says in a transaction process consisting of 3 activities, namely allocation, task processing and quality checks. So we have allocation, task processing and quality check. 9 employees including 5 male and 4 female. So we have 5 males and 4 females who are working. 2 of them are process leads, 4 perform processing, remaining 3 are quality auditors. Now out of the 4 female employees, 1 is a process lead. So we have 1 male processing lead and 1 female processing lead. 2 are processing executives. So we'll have 2 and 2 here, and then the remaining 1 is a quality auditor. So one of the female is quality auditor, whereas we have 2 male quality auditors. Now suppose the chance of allocating a task is equal among the process leads, equal among processes and equal among quality checks. What is the probability that the task is completely handled by a female employee? Now for this, required probability will be auditor has to be female. Here we have 2 people, out of which 1 is female. So this probability will be 1 by 2 into. Now for the second one, this probability will be simply 2 by 4, which again is 1 by 2. And for quality it is 1 by 3. And the process of choosing an employee across any process, it is independent. So this required probability is simply 1 by 12. Now question number 7 is success in a roll of 6-phase balanced die is defined as hitting a 6. So probability of success is 1 by 6. That means probability of failure is 5 by 6. Now it says let P denote probability of success if the probability of obtaining at least one success in n repeated rolls is greater than or equal to 0.9. So that means probability that X is greater than or equal to 1, it is greater than or equal to 0.9. What is the smallest possible value of n? Now we know that probability of x greater than or equal to 1, it is also written as 1 minus probability of x is equal to 0, and it should be greater than or equal to 0.9, or probability of x equal to 0, it should be less than or equal to 0.1. Now probability of x equal to 0 is nc0, p to the power 0, q to the power n, and will be less than 0.1. Now q is 5 by 6 to the power n, and will be less than 0.1. Now if we take log and solve, we'll get this n, it should be greater than or equal to 12 point something. So basically the smallest possible value of n must be 13, and that is the answer to this question. Now question number 10 is two numbers x and y are chosen at random from the set 1, 2, 3 up to 30. Then the probability that x square minus y square is divisible by 3 is. Now first we'll find total number of case. So total number of case will be 30C2. So from these 30 numbers we can select any two numbers, and it will be given by 30 into 29 divided by 2. Now we have to find the probability that this x square minus y square is divisible by 3. So we can write x square minus y square as x minus y and x plus y. Now what we'll do is we'll partition this set in 3 subsets. Set 1, which are multiple of 3. So it'll be 3, 6, 9 up to 30. Then numbers which leave the remainder 1. So it'll be 1, 4, 7. And then numbers which leave the remainder 2. So it'll be 2, 5, 8 and such numbers. So there'll be 10 elements in the first set, 10 elements in the second set, and 10 elements in the third set. Now this number x square minus y square, it'll be divisible by 3 when either both the numbers, they belong to the same set. So either it can be from this first set or from the second one or from the third one. So it can be any of the set 3C1, and from this set we can select any two numbers in 10C two ways. Or when x plus y is divisible by 3. Now x plus y will be divisible by 3 when either we choose elements from this set, so which we have already done in the first case, or when we choose one element from this set and another element from this second set. So it will be 10C1 into 10C1. So probability that this number is divisible by 3 is 3 into 10C2. Now 10C2 is 45 plus 100 upon 15 into 29. So it will be 3 and 9, 20. So it will be 47 upon 87, and that's your option number D. Now question number 26 is, in a factory there are 3 machines X, Y and Z, and they produce 1000, 2000 and 3000 bolts every day. Now the probability that bolt is manufactured by X is 1000 by 6000, so it will be 1 by 6, Y is 2 by 6 and Z is 3 by 6. Now defective percentage of each of these machines are 1, 1.5 and 2. So probability of getting defective from X, it is 1 by 100. Defective from Y, it is 1.5 by 100. And defective from Z, it is 2 by 100. Now it says a bolt is found to be defective. What is the probability that this bolt is produced in machine X? So it's a Bayes theorem question. So if it is defective, it came from machine X. So we'll take this case in the numerator. So it will be 1 by 6 into 1 by 100 upon 1 by 6 into 1 by 100 plus 2 by 6 into 1.5 by 100 plus 3 by 6 into 2 by 100. So this 100 into 6 will cancel. So we'll write this probability as 1 upon, and this is 1 plus 3 plus 6. So it will be simply 1 by 10, and which is none of these. Option number D. Now question number 2 is, the bleaching stage of a pulp manufacturing process needs to be executed in such a way to achieve a pulp brightness of 50, pulp whiteness of 80 and viscosity of 30. This can be done by controlling the chemical flow, duration and temperature of the bleaching process, and then we are given some equations. First we need to write these linear equations. So let chemical flow be x, duration be y and temperature be z. Now for brightness we'll write 2 times chemical flow, so it will be 2x minus 15y plus z, and it is equal to brightness. Now what is the required brightness? Required pulp brightness is 50, so it will be equal to 50. Now the second equation will be x minus 25y plus 2z, and it will be equal to this whiteness, which is 80, and then this third equation, which is 5x plus 20y minus z, and this is equal to 30. Now we need to find the value of x, y and z. So first we'll add these two equations. So we'll add them, we'll get 7x plus 5y, and it is equal to 80, and that's our first equation. Now we'll multiply this third equation with 2, and then we'll add them again. So it'll be 11x, and then 40 minus 25 will be 15, so it'll be 15y, 2z and minus 2z will cancel, and it'll be 60 plus 80 will be 140. So that's our second equation. Now we need to eliminate y, so we'll multiply first with 3, so we'll get 21x plus 15y equals 240. Now we'll subtract this, 15y will cancel, we'll get 10x equals 100. So value of x should be 10. So value of x is 10. Now we'll put x as 10, we'll get 5y equals 10. We'll get value of y as 2, and if x is 10 and y is 2, so we'll write 20 minus 30, so it'll be minus 10, value of z will be 60. Now part B is, there are 4 red, 5 black and 6 blue balls in an urn. So we have this urn. So here we have 4 red, 5 black and 6 blue balls. Now 4 balls are drawn at random without replacement from this urn. What is the probability that these 4 balls will contain at least 1 ball of each color? Now first we'll find total number of elements in sample space. So altogether we have 15 balls, and from these 15 balls we can select 4 balls in 15C 4 ways. Now we'll need to find number of favorable outcomes. Now the outcomes will be favorable when these 4 balls, they contain at least 1 ball of each color. So there'll be 3 cases. Either it'll have 2 red, 1 black and 1 blue, or 1 red, 2 black and 1 blue, or 1 red, 1 black and 2 blue. Now 2 red will be simply 4C2, 1 black 5C1 and 1 blue 6C1 plus 4C1, 5C2, 6C1 plus 4C1 into 5C1 into 6C2. Now 4C2 is 6, 5C1 is 5 and 6C1 is 6. Now 4C1 is 4, 5C2 is 10 and 6C1 is 6 plus 4C1 is 4, 5C1 is 5 and 6C2 is 15. We can take 60 common. So we'll take 60 common. We'll get 3 plus 4 plus 5. So it'll be 12 into 60. Now this required probability will be number of favorable outcomes, which is 12 into 60 upon total outcomes, which is 15 C4, 15, 14, 13 and 12, and then 4, 3, 2 and 1. So 12 will cancel, 15, this is 4, 2 is 7, so it will be 48 upon 91. So the required probability is 48 by 91. Now this part B is, a biased coin has probability P of coming up heads on any toss. So we have taken PH as P. When it is tossed twice, it is known that probability heads tails or heads heads is 5 by 6. Now we can write this probability as probability HT plus probability HH, and this is 5 by 6. Now since events are independent, we can write PH into PT, PH into PH, and this is 5 by 6. Now we'll take PH common, so it'll be PH, and then here will be PT plus PH, and this is 5 by 6. Now tails and heads, they are mutually exclusive and exhaustive. So PT plus PH will be 1. So value of PH, which is P, is 5 by 6. So from here we'll say value of P is 5 by 6. Now it says if the same coin is tossed 3 times, then find the probability of observing exactly 2 heads. So probability of getting exactly 2 heads, this probability is 3C2, P to the power 2 and Q to the power 1. So it will be 3C2. Now what is P? P is 5 by 6. So it will be 5 by 6 square into 1 by 6. Now 3C2 is 3. So it will be 25 upon 36. And this is 1 by 6. So this probability will be 25 upon 72. Now the next question is, a pair of fair dice are rolled independently 3 times. So in this case we have n equals 3. The probability of getting a score of exactly 9 twice. So getting a sum 9, getting the sum exactly 9, it is yours. Getting the sum 9, it's your success. And probability of success will be, now we'll get 9 when we have 3, 6 or 4, 5, 5, 4 and 6, 3. So this probability will be 4 by 36 or 1 by 9, and probability of failure will be 8 by 9. Now it says out of these 3 turns, we should get exactly 9 twice. So we need to find probability when the value of x is 2. So it will be 3C2, P2 and Q. So it will be 3. Now P square is 1 by 81 and this is 8 by 9. So this probability will be 8 by 243 and that's your option B. Now fourth question is, a policeman fires 3 bullets on a dacoit. The probability that dacoit will be killed by 1 bullet is 0.7. What is the probability that dacoit is still alive? The dacoit is still alive if none of the bullets hit him. The probability that dacoit is still alive will be this P naught whole cube. So it will be 0.3 cube and there will be 0.027 and that's your option C. Now here the question is, a casting manufacturing company supplies metallic casting to an automobile company. The automobile company inspects every casting and rejects the casting if found defective. Now suppose a batch of 940 casting is supplied by manufacturer containing 70 defective. What is the chance that first and second casting inspected are defective and third is good? Now if first is defective, then its probability will be 70 divided by 950. Now for second to be defective, we'll have 69 by 949. And if third is good, we'll have 950 minus 70 and there'll be 880 by 948. And this value is 0.000497 and which is none of the above. And that's your option D. Now here the question is, let E, F and G be 3 events having probabilities 1 by 8, 1 by 6 and 1 by 4 and their intersection is 1 by 10. Then which of the following is correct? So we have 3 events E, F and G. So this is E, F and G. So let this be E, this is F and let this be G. Now it is given that probability of E is 1 by 8, probability of F is 1 by 6 and probability of G is 1 by 4 and their intersection it is given as 1 by 10. Then which of the following is correct? Now we know that probability of E intersection F will be less than or equal to minimum of probability of E and F, and in between E and F the smaller value is 1 by 8, so it will be always less than 1 by 8. In the same way, probability of F intersection G will be less than smaller value between F and G, which is 1 by 6, and the same way probability of E intersection G will be less than or equal to 1 by 8. Now if we look at probability of E union F union G, we know that this probability will always be less than probability of E plus probability of F plus probability of G. Now probability of E is 1 by 8, F is 1 by 6, and this is 1 by 4. Now this is 24, 3, 4 and 6. So it will be simply 13 by 24. So this probability of E union F union G, it is less than or equal to 13 by 24, and that's your option C. Now if we look at this probability, which is probability of E intersection F intersection G naught. Now probability of E intersection F intersection G naught is actually this probability. This probability is equal to probability of E intersection F minus probability of E intersection F intersection G. Now this is probability of E intersection F minus, and this probability it is 1 by 10. Now we know that probability of E intersection F, it is always less than or equal to 1 by 8. So its maximum value is 1 by 8. So it will always be less than or equal to 1 by 8 minus 1 by 10, which is 1 by 40. That means this option A is also correct. Now we look at this option B. Then option B is probability of E complement intersection F intersection G. Now it will again be probability of F intersection G minus probability of E intersection F intersection G. Now maximum value of F intersection G is 1 by 6. So it will always be less than or equal to 1 by 6 minus, and this intersection is 1 by 10. So it will be 4 by 60, which is 1 by 50. So that means this option B is also correct. Now if we look at this probability, which is E naught intersection F naught intersection G naught. So it will be this region, and this probability will be given by 1 minus probability of E union G union F. Now this probability will be minimum when this value is maximum. So it will always be greater than or equal to 1 minus 13 by 24, which is 11 by 24. So that means this option D is incorrect.